So we're looking at system of mass application, one box on a table with or without friction, so we will involve friction. This guy is obviously just going to fall straight down, so just going back to the force of gravity type problems that we looked at, right? And so we've got a pulley involved. One of the things about this, so obviously there's got to be some connecting cord between whatever this object on the table is and the hanging mass. But so in terms of wording, I don't want you to get confused. They'll always talk about the pulley being massless and frictionless, and then this cord being massless. Meaning, so we don't want to involve, right, because you could have a really heavy chain here, and that's definitely going to change how this whole system works. So we ignore the mass of whatever this rope or cord is, and we ignore any friction in the pulley, always. Now, even if they don't say it, we ignore it. But if you happen to see that as part of, the problem, don't get confused about what that is. I'm not sure what this little gray box is in front of the boy, because that's not my picture. So first, with no friction. So here's your setup. Now, I took this, I think, from the physics classroom, or I could be wrong. But after this, I basically took the notes page that they made and I put it in sequence, as you'll see. But I want to kind of just talk about it together first. So there's no friction to begin with, right? So that obviously only applies to M1. So you need to make a force diagram, right, for each object. And so that would be your first step. And so why this is a Newton's third law, because there's tension acting in this cord to the right. There's a normal force up, and we have the weight down, right? And there's no friction. Friction would be to the left, but there's no friction. So obviously the only thing different is if there is friction, we would add friction to the left. Now for the hanging one. Now, what I would suggest, again, that sometimes things go against what I've told you guys all year. I'm making to the right positive, I'm making to the left negative for this guy. But when I do these problems, you can do it either way. You can be consistent, and you can say, well, up's positive, I'm keeping it positive, or you can say down is positive. Because right, if this is the setup, this box doesn't have the ability to make this box rise. Right? It would just stay there, right? So we know that this thing is only going to go down. So I'm going to do it this way just because I think the notes that go behind everything I've covered up is doing it this way also. But we know there's tension up on M2, and obviously there's weight down, right? And so for these problems, the only thing that's going to change is right here, friction could be involved or it's not involved. So then what do? Well, we set up for object 1, mass 1, the two equations. Sum of the forces in the x equal m1a. With no friction, right, we don't need this. And we know that it's only going to move in this direction, and it's going to accelerate in this direction. Right now, it doesn't matter, with no friction, so there's no resistive force to the right. This mass can be anything. It doesn't have to be that this mass has to be greater than this mass. Right? So don't, like if this was 2 and this was 20, it's still going to move. It doesn't matter that because the and this is the other thing, the accelerating force that makes this whole thing slide to the right and this to go down is this force. Right? This is the force that makes the whole thing move. Now, the force of tension, right, this is why it's a Newton's third law problem, because this tension force is the same tension force between the two objects. That's that Newton's third law pair of force. And so while W2 is down and tension is up, right, then when I look at this and I know that these tensions are the same, there's no resisting force to these two things moving, right? And so they're going to move. Which camera am I looking at? Right? One's going to go down, and they're going to go together, right? Okay. So Now we know that this is going to equal, in the y direction, this guy's not going to move up and down, so this is going to equal 0. And you have the normal force minus the weight equals 0. The normal force equals the weight. It's not going to help us solve the problem at all because there's no friction. We don't really need it. And so it would be okay for you not to write it if you realize, okay, well, there's no friction. I don't need it. So here I do have tension equals M1A. Now the problem, ultimately what the problem is going to ask us to find is it's going to say solve for A and T. Right, those are the only things that we're going to solve for. Acceleration, well, it may ask for a velocity, but then you just go back to one of our motion equations. So I get to this equation right here. Now I want to look at mass 2. Sum of the forces in the x equal M2A. Well, are there any x forces? No, we don't need that. How about in the y? Yes, right? The y is the deal for this one. And so because I'm making down positive, right? W2 minus tension equals M2A. Now, if you were making, because normally when I do these, I actually do it the opposite way. But let's say you wanted to be consistent. You're like, well, you know what, Doc's always said up is positive. I'm sticking with that, down is negative. The only thing you would do differently here was you would say tension, right, is up is positive. Weight, negative, equals M2. But this is the key. This is the thing that people forget, is if you're making down negative, well, you've got to put in a negative sign right there. So I don't know which way is easier for you to remember. All right, that's a personal choice you get to make. I'm only doing it like this because if I remember correctly, that's what the notes thing here said. I could be completely wrong, but we'll see. So when I get to this point right here, right now I've got an equation with one unknown, two unknowns. Now I have an equation. So you got to remember, so we're solving for A and T, but the masses M1 and M2 will be given. Right? The masses will be given. So this is given. How do we calculate that? Well, we take M2 times G. So these are given. Right? Same value there. And so now we have T and A as our unknowns. We have T and A as our unknowns. So we have two equations with two unknowns. Can you solve that in math class? So if you're like, I don't know, I don't know if I know you understand what I'm talking about. Think back to Algebra 1 when your math teacher said 3x plus y equals 5, negative 2x plus 2y equals 10. Solve for x and y. Can you solve that equation? If your answer is yes, which I hope it is, that's all we're doing, right? And so I don't want orange. I think that's orange. Right now, what you can do, right? Because you'd have numbers here, but and again, this is a matter of choice. What I would do is, since I know that T is equal to M1 times A, well, here's T. So I'm going to put in M1 times A, right? Because T is equal to M1 times A. There's T. I put in M1 times A. M2A. Now what I'm going to do is I'm going to get, because there's an A here and an A here, and that A is one of my unknowns, I'm going to get all the A's on the same side. Right, so M1A on the right-hand side plus M2A. Now what do you think I'm going to do next? Use the F word, which is factoring. Right, now what you might have thought, factor out the unknown of A. And then, since we want to solve for A, well, I'm going to divide by the sum of the masses, and that's going to equal A. So now I can plug in the masses and I know, gee, I get the A. Once I get this value of A, well, then I'm going to plug in my answer right there and multiply it by M1. I've got the tension. Now, maybe, I don't know if that makes sense or not. It makes probably more sense when you start throwing in numbers, because I know you guys like numbers. But that's how you do a system like that with no friction. Questions? Okay, can I erase this? All right. So now, as you will see, again, I don't remember where I borrowed the slide from, but it sets it up for you, sets it up a little differently, just in terms of how they write it. But in the end, you see the substituting in. And so they did. I thought that's why I did it like this, because that's the way this slide had done it down, is chosen as positive, and you get this as the acceleration, right? And it's the same thing that we were just doing for the warm-up questions. You take the accelerating force. What's the accelerating force? It's the weight of box 2 that's hanging, and you divide it by the sum of the masses, right? That's exactly what we did for those couple bell work problems. It would work out to be the same if down was negative, because all the other signs would change accordingly, and it would still come out with the same result. Okay, now what if there is friction? Well, as you can see, friction is to the left. It changes oh so slightly, right? We're still solving for acceleration and tension force. You're still given M1 and M2 and the coefficient of static and kinetic friction, right? So make a force diagram. Normal force, weight 1, tension, friction, right? Nice thing about the one that's hanging, it's always going to be the same. Weight 2, tension, right? These will only be the only forces. Again, this slide makes down positive, or the acceleration positive, so I will continue with that. For this guy to the right, it's going to be positive. And so when I go to mass 1, and I say the sum of the forces in the X equal M1 times A, and now I need the sum of the forces in the Y, right, which are going to equal 0 because it's not moving up and down. Now I have tension to the right minus friction to the left equals M1 times A. The normal force minus the weight, right, weight 1 equals 0. The normal force equals weight 1, which is M1 times G, right? We don't know the number yet, but if it was given, we would plug it in and multiply by 10. We come over here and we say, okay, well, we've got a couple choices here. We're going to assume that it's moving, all right? But I want you to think about this for a minute. In after I show you the stuff with this particular problem, I'll show you what I'm talking about. But if you look at this, essentially, and this is what it does, is if we take this object and we put it on the table and we say, well, this object has friction, right? So what if we did this? Imagine this is an analogy to what we're doing. This is M1, right, with friction this way. Obviously the up and down forces, but tension this way. What if we take this and we bend it up so that it's actually on the table, right? And tension is here. So that's that Newton's third law. and the weight of this is the force to the right. So we're altering reality here, kind of, and we're making it, it's not hanging now, but it's on the table. This box doesn't have any friction, but this one does, right? Because essentially that's what that, instead of weight acting down as it does, we're pretending that the weight is actually pulling it to the right. And so in order for this to move, this force has to be greater than friction, right? Otherwise it doesn't move. So one of the things that you would check is the weight of box 2 greater than the force of static friction. Because if it's not, it can't move. Does that make sense? Right? If this force, right, of this hanging down, the force of gravity acting on it, because this is the guy that makes this thing move. Without that force, it doesn't move ever. That force has to be greater than the friction acting on this, because this force is the same force acting between the two objects. And so while they don't cancel out for the individual, they do cancel each other out for the system, because the whole system moves together. And so in order for this to move at all, the weight of this has to be greater than the friction acting on this, right? And so to make something move, we have to overcome static friction. So we're assuming that that's the case, right? And so it's going to move, and so then it is kinetic friction equals M1A. Well, how do we calculate the normal force? We know it's M1G equals M1A. Okay, so I need to get to that relationship right there. Well, actually, I need to take it one step farther, but I won't yet. And then, well, what about the hanging mass? The good part about the hanging mass is what you see is what you get. There's only the forces in the y direction. There's no x forces. And again, down's positive. Minus tension equals M2A. W2 is M2G. So this looks just like what we did with zero friction. The only thing that changes is this part right here, because there's friction, right? So now I get to this step again, right? What are my unknowns? Tension and acceleration. Tension and acceleration. What am I given? The coefficient, the mass, G, mass, G, mass. Right? So two equations, two unknowns, you do the same thing. But this one's a little trickier because you got an extra term here. So what I'm going to do is I'm going to do M1A. I'm going to add this to there's a minus, right? So I'm going to add it to the other side, M1G. And so what I have to do is put this in for T, right? So what does that look like? M2G minus, you do this in a different color, right? So it's M1A plus the coefficient of kinetic friction, M1G equals M2A. Now what do I have here? I have a big expression that doesn't have tension in it at all, but it has acceleration. So what do I want to do? Well, we know the masses, we know G's 10. The thing I don't know is A, but I have it here and I have it here. So we need to combine like terms, right? Remember learning that in algebra? Which means I need to get everything with an A on the other side, just like I did before. Everything else can stay where it is. So I'm going to take this term and bring it to the other side, right? And then this was what I had before on the other side. And what did I do? Well, I factored out the A. And now I want to solve for A. So that means I'm going to divide, right, both sides by the sum of the masses. But I have to do it to this side also. So that all cancels out. And now I have A. And what am I left with? Well, M2G, right? That's what I had for the one without friction, plus friction, divided by M1 plus M2. Now think about when we did what we did yesterday in the bell work problems we did. What did we do? We said for the first part, we have to find the acceleration of the system. We do that by taking the sum of the forces and dividing it by the total mass. Now, how is this related to this? right? Well, what do we have here? We have this force here, right? And this force here. That's the sum of the forces, right? And what are we dividing by? The total mass. Total mass is m1 plus m2, right? Did I forget something?
I have a question real quick.
I feel like I lost something there. Yeah, go ahead.
So would it be better to not factor out the mass from there? Because I know sometimes we factored out the mass to make it a little easier on ourselves. Would that not be the
Up
case
here?
here?
You mean do it from
No, in the step with the arrow by it where it says M2G minus M1A plus the coefficient of kinetic friction, mass 1,
Oh, you guys,
gravity. Yeah,
yeah,
that.
yeah. Hang on, but you guys realize what you let me do? I knew I'd catch my hair, but I didn't distribute the negative sign, right? I plugged this in for t, but I should have done it like this because that should, and I knew that made. I'm talking and looking at things. I'm like, what did I do wrong here? That should have been that, right? Because the accelerate with friction, the acceleration can't be bigger. That's right. But again, if we're not thinking about things, so I'm substituting all of this in here. Then I have to distribute this negative sign to this and this. That's why it's negative, right? And that's what it should look like. See what it might now, Aaron, I think what you're saying is, should I do this? Sorry, M2 minus UK M1, factor out the G. Is that what you meant, Aaron? Sorry.
Yeah.
Yeah, I would say you can, and it's perfectly fine because you know G is 10 for both. I would leave it like this. But again, you know, this is what you would see in a textbook. You wouldn't see this. It's not wrong, and you certainly can do it. Hold on, let me see what the chat says. So let me show you what. Oh, I can't do that. I keep forgetting. Can I get rid of this? And show you what it looks like. Right, so same deal. Your two equations, they get bigger because you've got an added term. And this is what it looks like. So it's the same, except now we subtract friction. The weight minus friction equals M1 plus M2. The accelerating force, right, is the sum of the forces divided by the sum of the masses. Same thing we did yesterday, same thing we did with the bellwork problem. Now, this is the analogy way. They call it the magic pulley because it bends the line of action of the force without affecting tension. Right, here's your force diagram. They show it just without friction. There's that connecting cord. And this is where they take this and they put it on the table. Here's your Newton's third law pair. This is the force, right? So you're basically rewriting the problem to be for both objects to be on the table, but you're making that pulling force to the right equal to this guy's weight. And then you're solving it just like what we did for the bellwork problem and what we did yesterday. Because the math is exactly the same. Right, and then when you set up the equations, you end up with this canceling out, and you have this divided by the sum of the masses to equal the acceleration. All right, we don't have a lot of time left, but I want to do at least one problem for you guys. Now, hopefully, between now and next Tuesday, which is a really long time, you'll see the similarities to do the problems. Now, I won't do this one, but again, think about the weight of this guy if there's friction, has to be greater than static friction to make this thing move, right? That's a very common multiple choice question that you want to remember. Right, so this is a continuation of the first part of the problem. So, ow, that hurt. Oh. So again, we got to find, this is pretty much what it's going to ask you to calculate every time. Right, so for just the sake of time, I'm going to kind of make my force diagram up here. There's friction this way, right? We're assuming that it was greater than kinetic friction, which is what the first part of this problem said. There's tension, there's the weight too, right? Those are my force diagrams. So for mass 1, sum of the forces in the x equal m1a, sum of the forces in the y equal 0. Force to the right, tension, minus force to the left, friction, equals m1a. Normal force minus weight of 1 equals 0. Normal force equals weight of 1, which we know the mass is 10, right? So 10 times 10 tells me that normal force is 100 newtons. Tell me if I'm going too fast. I don't want to try to keep you guys not being late to your next class. For mass 2, the good thing about the mass 2, the hanging mass, it's always going to be the same. Right? It's always going to be, so again, W2, if we're making down positive, minus tension equals M2 times A. So if I come over here and I say, okay, well, tension I don't know, coefficient of kinetic friction times normal force equals M1A, tension equals, coefficient of kinetic friction was 0.2, times the normal force, which we know is 100, equals M1, which was 10, times A. Right, what is that, 20? So now I get it to this point where I have just T and A, X and Y as my two variables. So I have to stop at this point right here, right? Because I've got two unknowns in this equation. So if I come over here to M2, how do we calculate the weight? We know it's M2 times G minus tension, which we don't know, equals M2 times A. M2 is 5 kilograms, right? So 5 kilograms times 10 minus T equals 5 kilograms times A. So that's 50 newtons minus T equals 5 kilograms times A. So I get to this point, I have my two equations, X and Y. So what do I want to do? Well, I want to take this one, right? And I would always pick the one on the table and solve it for tension. You can get rid of units at this point to make it kind of a little bit easier and more like what you're used to in Algebra 1. And just say, well, it's 10 times A plus 20. And then I come over here, and don't make the mistake that I made earlier, right? 50 minus 10A plus 20 equals 5A. So I got to remember, right, what I didn't remember last time was to distribute the negative sign, because it's really negative 10A minus 20 equals 5A. What you got to remember also, and I didn't say this in the beginning, is that the acceleration has got to be bigger than 0, right? And if we're using 10, it can't be greater than 10. And so that's what would have happened had I not caught my forgetting to distribute. When I plugged in numbers here, I would have got an answer greater than 10. It can't, if gravity is the thing that's causing it to move, unless we're going to Jupiter, it's not bigger than 10, right? So I'm going to add 10 to the other side, the 10a to the other side. Right, so it's 5a plus 10a, 30 equals 15a, a equals 2 meters per second squared. Right, this has to be between 0 and 10. And then I simply take my value for a and I plug it in right there. 10 times 2 plus 20, 20 plus 20 equals 40 newtons. Every problem, that's as hard as it gets because that's the one that involves friction. And so any problem that doesn't involve friction, we just get rid of that term and we have T equals 10 times A, right? And then if there was no friction, it would be just 10 times the value of A.